Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so very happy to have Andrew Holroyd tell us about self-organizing cellular automata.
Okay, well, thank you for coming, everyone. So I'll try to tell you some of what I've been getting up to with Janko Gravner, who's at UC Davis and who was visiting here last month. So I don't usually do this, but I'm going to start with quite a lot of background, motivation, showing you pictures. Some might call it waffle before I get down to things, but rest assured there will be some theorems coming. And the reason I do this is because the motivation for what we're doing is maybe not completely obvious to begin with. So that's what I'll try to show you. So let's talk about cellular automata. So this is a subject with quite a long history. So certainly von Neumann and Ulam considered cellular automata. And perhaps the most famous example is Conway's game of life, which probably most people have heard of already, but in case you haven't, you work on the square lattice Z2, and elements of Z2 are called cells, and each cell is either alive or dead, has two states. Sometimes we call them 1 and 0. And so you have some configuration of alive and dead cells, and then there's an update rule, which in this case is a dead cell becomes alive if it has if it has exactly 3 living neighbors, and neighbors here refers to the 8 other cells at L infinity distance 1 from it, so-called Moore neighborhood. And if a cell is already alive, then it stays alive if and only if it has 2 or 3 living neighbors. Otherwise it dies, and you update everything simultaneously in discrete time. So you update every cell according to these rules, you get a new configuration, and so on. So there we go. Okay. So yeah, so here's a very famous example of Conway's life. You start with these cells alive, and you apply the update rule, so each cell sees how many living neighbors it has, and the second step you have this, and the third step you have this, and so on, and it turns out this is called a glider, so this shape just moves diagonally, and there's a huge amount of work that people have done in setting up very special configurations in Conway's life and other cellular automata to do specific things. So for example, this is a configuration that computes twin primes. So a very, very complicated thing, and it does all sorts of complicated stuff. And after a while, there'll be some output stream coming out here, and the locations of these gliders represent the locations of all twin primes. Not known whether there are infinitely many or not, and thanks to an extraordinary algorithm called hash life, it's possible to run these things at extraordinary speed. So this is already getting to millions of iterations.
You know that if you define twins to be within 70 million of each other, then they are.
Yeah, so that was the initial configuration. Here is I changed one cell. I changed the state of one cell in the initial configuration. And what happens if you run that? Well, so it starts off looking good, but then after a while you realize something is wrong. And, well, I've no idea what it's doing, but it's certainly not computing twin primes. And probably the best description of this is chaos, although very difficult.
This configuration
no idea. Unlikely in this particular case, I think, but no idea. So yeah, so somehow the point is, a lot is known about what you can do if you start from a very, very specific situation, and much less is known about typical initial configurations. For example, what happens if you take a uniformly random initial configuration on Z2 and run life? I don't think anyone has any idea what the answer to that question is. I might come back to that later. There we go. Hopefully I won't have to go through that again. Yeah, that was Conway's life. So, yeah, so it turns out a lot of the surprising and interesting things that cellular automata can do can already be seen in one-dimensional models, so that's what we'll focus on. So one-dimensional cellular automaton rules with a quiescent state 0, so that just means there's some state, so that if all cells are in state 0, then the next time they're all in state 0 as well. And I'm particularly interested in what happens if you start from a seed, which is an initial configuration with only finitely many non-zeros. And especially what I'm really aiming for is what happens with typical, i.e. random seeds. So, okay, let's look at some examples. So, some cellular automaton rules, it turns out, are completely predictable in a strong sense, which I'll explain. So one example is so-called 1 or 3 rule. So like to remember it's in one dimension. So lambda tx will denote the state of cell x at time t. And if you want to know the state of x at t plus 1, then it depends on 3 things. It depends on itself and its left and right neighbors at the previous time step. And it's simply the states are 0 and 1. And it's 1 if the number of if the sum of these is 1 or 3, otherwise it's 0. And of course, another way of saying that is it's just the sum of these three things modulo 2. Okay, so we normally draw these things with time going down the page. So here's a summary of the rule. If you have 1 or 3 of these 3 guys are black, then the one below is black. So okay, here's a picture of what that does, starting from a single 1 at the top. So does everyone understand the picture? So time is going downwards, and the universe is one-dimensional. So we started off at this time with a single black dot, and then it's time 2, time 3, etc. Now this picture, it turns out, is completely understandable in a certain sense. So it has a fractal structure, a self-similar structure, and it's possible to write down a recursive description of it, where this section here is composed of smaller sections that you've seen earlier on, and so on. So no mystery about this, really. What happens if you start from a different seed? So here was a random seed of length 12 or something like that. Well, essentially the picture is very similar. So you still have this fractal shape, but it's thickened a little bit. And also the configurations in the thickened part are predictable, it turns out. So all these little configurations here are the same, and similarly everywhere you see it. So again, this is completely predictable. It's something we call replication, and I'll come back to define things like this more carefully later. But essentially every seed gives a similar picture for this particular rule. And there's a very simple reason for it in this case, because this rule is additive. So remember, it was the state of a cell is the sum of the 3 above it modulo 2. And as a consequence of this, very easy to prove, if you want to know what happens for any initial seed, for example, the seed consisting of these 3 sites here being 1, all you have to do is draw the triangles, the fractal triangles that you get starting from a single 1 from those 3 places, superimpose them, and then add the modulo 2, and that gives you the answer. So everything here is provable. So on the other hand, here's a rule that behaves completely differently. This is rule 30. This is Wolfram's numbering system for elementary one-dimensional rules. The details don't really matter. I mean, if you see exactly 1, 1, then you become a 1, and also if you see this, you become a 1. So here's what happens from a single seed, sorry, a single 1. So you might say the best description for what's going on here is chaos, although kind of it's not quite as simple as that, because you can see things are periodic along the left-hand side. But certainly there's no simple formula that anyone knows to predict what happens a long way down. And not surprisingly, if you start from some other seed like this one, then you still get apparent chaos. And even in one dimension, some of these rules are sufficiently complex that people have proved that they are Turing complete, capable of universal computation. So in particular, rule 110, which is another one of these ones, Matthew Cook proved that it's Turing complete, previously conjectured by Wolfram. But once again, this is, the theorem says you can produce a Turing machine if you set things up exactly right to begin with. That's very important. So it's nothing to do with what happens for a typical initial condition. Now, in some ways, the most interesting types of rules are ones which can exhibit different types of behavior depending on how you start them. And this is such an example, so-called exactly one rule. It's simply, you look at yourself and your two neighbors left and right, and if you see exactly 1, then you become a 1. And here's what it does from a single 1. Looks kind of similar to the previous pictures, a nice fractal. Here's what it does from another small seed, also what we call replication, so a nice fractal, although it's a little bit more complicated because the configuration here is not the same as the one here. But still, this is completely analyzable. On the other hand, if you start from certain other small seeds like this one, you get apparent chaos in the sense that there doesn't seem to be any way to predict what happens in the middle. And also from, again, same rule, from some specifically chosen seeds, you can get something else, a periodic pattern in space and time. And you can even get mixtures of several of these things. So here it's periodic in a non-trivial wedge at the side, but apparently chaotic in the middle. And rather amazingly, some of these sort of things can be proved. So Ravner and Griffith recently proved that many of these behaviors for this particular rule I just showed you, exactly one, replication, periodicity, some of these mixtures occur for infinitely many initial seeds, even an exponentially growing family of seeds, exponentially growing in length. But the conjecture here, and this is sort of the point I want to get to, the conjecture here would be that chaos is the typical thing, in the sense that if you start from a uniformly random seed of length L, in other words, all 2 to the L binary strings equally likely, then with high probability, with probability tending to 1, you see chaos, at least within some cone or wedge. And what does chaos mean? Well, yeah, there's no universally accepted definition in this subject for what chaos ought to mean. But here's one thing you could say, for example, that if you look at local patterns, strings of length 10, and look at the densities of them, then they converge to something. And if you look at all possible lengths, they converge to a non-trivial probability measure, which should have some sort of mixing properties. So what happens over here should be asymptotically independent of what happens over here. So you can write down more precise versions of this. The conjecture would be that something like this typically happens. And by the way, nothing like this is proved for any cellular automaton that I know of, even though this sort of behavior seems very, very common. And you might argue this isn't quite strong enough because somehow chaos implies it's not predictable as well. There's no simple formula. But in any case, even nothing like this is proved. Okay, so you might at least imagine that something like this situation is a universal law, something akin to the second law of thermodynamics, that if some cellular automaton rule is capable of producing chaos, whatever that means, then chaos ought to be the norm, in the sense that from long random seeds, you should get chaos with high probability. And it's easy to postulate a mechanism for this where somehow chaos can start from some local configuration, and once it starts, it should win. It should take over everything else. Chaos should take over. So you might guess this is what always happens, but it turns out that's wrong. So some cellular automata are self-organizing in the sense that the opposite thing holds, and the first real evidence we know about for this is another paper by Grafner and Griffiths. So they showed that for certain one-dimensional rules, some seeds give you chaos, and but apparently almost all long seeds give you predictable behavior, but predictable in a non-trivial way. And our goal here is to give a rigorous version of this phenomenon. And now I want to be careful because a lot of the words on this slide you hear all the time with elaborate claims, sometimes not with much substance behind them, not necessarily, and I don't want to fall into that same trap. So what we're proving is something very specific about very specific models, and this is just motivation, but I just want to give you the idea that we're motivated by some kind of deep questions, even if they're not necessarily mathematical questions. So this is where we're coming from. And I should also mention, in a slightly similar vein to this, there's this famous or infamous positive rate problem. So there's a result by Gatch, very, very difficult proof, so difficult that very few people other than the author claim to understand it. But so Larry Gray has written this thing in which he claims to understand it. You would have to ask him. I don't understand. So the claim is that there exists a one-dimensional cellular automaton model, so that if you run it but with random noise, so you take an epsilon, and at each step, every transition, you have probability epsilon of making an error and changing to a random state, then there exists a rule which nonetheless has multiple stationary distributions. Think of it as like a plus phase and a minus phase. So in
this to be running on the infinite.
Yeah, that's right. That's exactly. So for two-dimensional models, it's well known that something like that can happen. For instance, for the Ising model, but in one dimension, it's apparently true, but very, very difficult thing.
Still controversial.
Yes. Okay, so that's an aside, but it's the same sort of thing that we're trying to get at. Okay, can cellular automata or other similar systems do complex things even in the presence of randomness? Okay, so what we prove is, and I'll have to come back and define terms here, but what we prove is that for one-dimensional cellular automata in a certain class, started from a uniformly random seed, with probability going to 1, you have replication, which I'll have to define, but you should think of it as these fractal-like pictures. While some seeds do not give you replication. They provably do something more complex and apparently chaos in some cases, although we aren't able to prove chaos. Okay, so obviously for this to be a theorem, I have to tell you what each of these three things means: certain class, replication, and more complex behavior. Okay, so I'll give you one simple example of a rule which our theorem applies to. First of all, it'll have 3 states, 0, 1, or 2, and 0 will be white, 1 will be black or gray, 2 will be red. And your state at time t plus 1 is given by a function of the 3 things above you, yourself and your 2 neighbors at the previous time. And the function f of a, b, c is if you see 1 or 3 1s in your neighborhood, then you're 1. And otherwise, you look at a and c, so you just look at your left and right neighbor at the previous time. If exactly one of them is a 2, then you become a 2, otherwise you become a 0. So the way you can think of it is that the 1s are performing this 1 or 3 rule, which was the nice predictable one, the additive one, and the 2s try to perform XOR just on the points not occupied by 1. So XOR meaning they look at their left and right neighbors and take the exclusive OR of them. Okay, so that's the rule. So here's an example of what it does, starting from a very simple seed. This is an apparently chaotic picture, although we can never prove that. So the grey is the 1s, and they are just doing the additive 1 or 3 rule, so you can think of them as being decided on to begin with, and then the 2s, the red things, are somehow seeping through. But here's what happens for a typical long seed. So this is a random seed of length 30 or something like that. Totally different. This is replication. Basically, you have this fractal picture that we saw at the beginning, except thickened, and a few reds around the edges. And you can already see how we might go about proving something like this. And here are some pictures where you don't have replication. You provably have something else. Here, this is an example of something we called quasi-replication. I'll come back to what that means. There's some non-trivial fractal configuration of 2s. And here's another picture of quasi-replication. Turns out this picture as well can be completely analyzed, this specific seed. One can completely say what's going on here. I'll come back to that. Okay, so what's replication? So first of all, let lambda be the 1 or 3, the support of the 1 or 3 rule started from a single 1. So it's this nice fractal triangle thing we saw before. And let lambda of R be the set of all space-time points within distance R of that set. Okay, so just fatten the fractal by R. And we say the configuration is a replicator of thickness R and ether eta, where eta is a doubly periodic configuration of 0s and 2s on Z2. So space and time periodic, if every bounded component of the complement of lambda R is filled with a translate of the ether eta. So here's the picture you should have in mind. You have the black, which is the nice fractal triangle, and you shrink away from it by distance R, and you get these triangular spaces, and each of those is filled with a doubly periodic picture ether, doubly periodic pattern eta, which we call the ether. So in particular, for example, this implies, if you have such a configuration, that the density of the whole thing is just the density of eta, because these white triangles occupy proportion 1 of the area. They have density 1 in the forward light cone of the origin, because the black is just a fractal. So it has a non-trivial fractal dimension. And also, if you have such a situation, it turns out if you have any replicator, it turns out it's possible to describe the configuration everywhere, even close to lambda, even within lambda R. And that's because in these regions in between the white triangles, those have bounded width now, width about R. So there's only finitely many configurations that you can see in those places. And it turns out on the basis of that, you can describe the whole thing. And this is work by Gravner, Griffith, and Pelfrey. So anyway, the takeaway message is that if you have a replicator, everything is predictable. So here are some pictures. This one we already saw. This is a replicator with 0 ether. You have the gray fractal, and you have the white triangles, and in the white triangles you just have zeros. And this is a picture of a replicator with a different ether. you have some thickened version of the fractal, and each of these voids is filled with this doubly periodic picture. This is for another rule that our theorem applies to. And this is now for the same rule as the previous picture. That's a different ether, which you can get, so a different doubly periodic configuration. And that would be a replicator with zero ether as well, because you're allowed to have complicated things happening on the fractal as long as these triangles contain zeros in this case. And according to our definition, this is something which is not a replicator, because we claim, and again, this is another rule that our theorem applies to, but this is an exceptional seed. Our definition said you're only allowed to have a single ether. You have to see it everywhere for the particular seed. So, okay, back to my theorem. So here's what the claim now says. It says for certain cellular automata, if you take a uniformly random seed of length L, then there exists a random number RL, which could be infinite, and a random ether, eta L, so that you see a replicator with thickness RL plus L and ether eta L. And furthermore, so, okay, if RL was infinity, then this statement is vacuous, because it says the distance that you pull away from the fractal is infinity. But the probability that RL is infinity goes to 0. And even RL is tight. So the distance that you move away from the fractal is basically just L plus something not very large. And the same holds even if we change some of the zeros and the twos, some of the zeros to twos in the initial configuration with the same ether and the same R. Okay, so that's the conclusion of the theorem. And now I have to tell you which things it applies to. So think about a configuration of the 1 or 3 rule. Again, this is the simple additive rule. And we'll define an empty path is just a path of zeros in the configuration that takes steps down or down left or down right. And an empty diagonal path is a path of zeros where you only take diagonal steps, diagonally to the left, diagonally to the right. And don't worry about this too much, but we also define a wide path is a path which is empty, but you can't move diagonally between two ones like this. Okay, so the definition is we have 3 states, which we call 0, 1, or 2, 0, 1, and 2. Looks like there's a bracket missing here. We have a range 2 rule, which means you can look at yourself or your 2 neighbors or your 2 next nearest neighbors at the previous time. And the assumptions are, if you just look at ones, then they obey the 1 or 3 rule. If you're blind to the difference between zeros and twos, then the cellular automaton obeys this simple 1 or 3 rule. And the key thing is information about the distinction between zeros and twos can only pass along diagonal paths. So the ones, you can think of them as being there already because they just come from this very simple rule that we know about. And then anything that's white here could be either a 0 or 2. And how do you decide? So if you want to know whether this is a 0 or a 2, then it's going to depend on stuff above it, but it's not allowed to depend on whether that's a 0 or a 2, because it's only allowed to look diagonally. And so here, whether this is a 0 or a 2 can depend on whether that's a 0 or a 2, because that's a diagonal step. And it can also depend on the fact that there is a 1 above it. No reason to prevent that. Okay, but information can only flow along diagonal paths. Okay, so
empty means 0?
yes, empty means of zeros in the 1 or 3 guy. Okay, so I won't write down the formal definition, but you can look at the paper if you want to see it. So, okay, our condition says for one of these things that is either compliant with diagonal paths or wide paths we can do as well. This is the conclusion. And that includes all the pictures I showed you at the beginning. So what about this provably more complex behavior? So, okay, I'll be fairly brief about this. So we call a configuration a quasi-replicator if there's some exceptional set of space-time points so that each bounded component of its complement is filled with an eta. And furthermore, this exceptional set, if you scale it by a to the n by some fixed number a, which is normally 2, but not always, then it converges to something of non-trivial Hausdorff dimension. So it's really a fractal. And yeah, so it turns out you can prove, or rather Grafner, Griffith, and Pelfrey can prove that certain specific seeds are quasi-replicators by inductive schemes. So here's a very simple example of a quasi-replicator. So the exceptional set is the gray and the red together, and you know, you can completely understand this picture because you can say what happens here and what happens here, and there's some inductive recursive scheme. You can prove it, and it's not a replicator on the other hand. And rather more surprisingly, examples like this you can sometimes prove are quasi-replicators as well. Much less obvious what's happening here from the picture, but it is completely predictable. That's a bigger picture of the previous one. And here's another example of a replicator where the ether, a quasi-replicator where the ether is this non-trivial periodic pattern, but it has these disturbances which nevertheless only live on a thing of non-trivial fractal dimension. So they occupy zero density in the bulk, these disturbances. And yeah, so for specific cases, it's often very, very hard to decide whether you have a quasi-replicator or chaos. So for instance here we think it's probably chaotic, but we have no way to tell for sure. Right, so that's the last part of the theorem, that for many of these rules that the first part applies to, some seeds are quasi-replicators, and also some are apparently chaotic, but of course we can't prove that part. Okay, so, and we can say some additional things as well. So you saw in this pink picture of the rule that I called piggyback, which I didn't define for you, and I'm not going to, that you can have different ethers, different periodic patterns in the triangles. And basically, if you see some ether at all, if for some ether eta, it's possible for some seed that you get that ether and this RL is finite, then you see it with positive lim-inf as the length of the seed goes to infinity. And in fact, we can compute rigorous lower bounds on probabilities of particular ethers. So for instance, for this rule, we know that at least 100 ethers have non-trivial lim-infs for long seeds, and we believe that there are infinitely many. Also, we can prove this is a slightly different kind of result. If you take a seed and you change zeros to twos, some zeros to twos in the initial seed, then I already said it doesn't affect the ether or the R, but in fact it has no effect at all within some region about log L from the forward light cone. Okay, so what? Yeah, I should briefly mention this. So although perhaps the particular cellular automaton rules that I'm looking at may seem a bit contrived, it turns out they are relevant to other things people are interested in. So they have implications for certain two-dimensional rules that people are definitely interested in, solidification rules, via something called extremal boundary dynamics. So I probably won't have time to discuss that, but that was part of our motivation. So the key tool is one of my other favorite topics, percolation. So we do percolation on the space-time configuration of a cellular automaton, and it's this 1 or 3 cellular automaton, this particularly nice one. So here's a theorem. So if you take, again, the 1 or 3 rule, this additive cellular automaton rule, and you start it from a uniformly random configuration on the whole of Z. So in other words, you take fair coin flips, 0s and 1s on Z, and you run it, then, well, diagonal paths do not percolate in the sense that the probability that there is a diagonal path from time 0, so anywhere along the top line, to a particular point at time t, distance t down, goes to 0, decays exponentially with t. And the same applies to wide paths as well, which I didn't talk about tonight. So here's the picture. Here are, here's the set of points reachable from diagonal paths, reachable by diagonal paths from this interval, as for wide paths. And on the other hand, if you look at empty paths, which were the ones that can go down and diagonally in the 2 directions, then they do percolate. So the probability I should have said, yeah, there's an infinity missing here. It should say the probability there exists an infinite empty path from the origin is positive. And that's the picture. Okay, so how do we prove this? So it's, on the face of it, potentially very tricky, because this is a highly dependent percolation problem. We're looking at the space-time configuration of the evolution starting from a random configuration, and that's not IID in any way. It's highly dependent because everything is a deterministic function of what happens on the first line. So problems like this, highly dependent percolation problems, in some cases are very, very tough indeed. So coordinate percolation, Winkler percolation are some of the words, and there are a number of impressive results here. I particularly mentioned this recent result by Basu and Sly, which is on a model of this kind. But it turns out in this case we're lucky. It's not one of the cases where it's fiendishly difficult to analyze, and there are some other similarly well-behaved cases that have been found as well, including these. So the key idea is this. So the space-time configuration is highly dependent, but on the other hand, we can find certain sets within it, sets of space-time points, where we see independent randomness. So suppose, don't worry about all the notation so much, let me just explain. So suppose you start from an initial configuration in which some set is uniformly random, some set A, not necessarily the whole of Z, and suppose you are interested in some set of space-time points down here. Well, because the rule itself is simply this additive cellular automaton rule, the configuration that you see down here on S is a linear function of the initial configuration, linear function modulo 2. And what we want to do is basically find cases where the matrix that tells you what linear function it is upper triangular with 1s on the diagonal. Okay, so if that's the case, then this set of sites you're looking at down here will itself be uniformly random. If you just look at that set of sites, you see IID coin flips, fair coin flips. And what that basically involves, how do you find out what the matrix is? Well, it basically comes down to just looking at the configuration started from a single 1. That's where all the information lies, and this, this picture one can understand. Okay, so that's the idea. So we sort of now try to find the right sort of percolation arguments that will adapt to this setting. So here's the proof of no percolation for diagonal paths. So Okay, here's a diagonal path of length t. The number of such paths is 2 to the t, starting from the origin. And I claim for any given path, the probability that it's empty, in other words, the probability that all the sites in it are zeros, is exactly at 2 to the minus t, as if it were everything IID coin flips. And the reason is a dual assignment. So for any given path, yeah, so I guess I didn't really define what these pink arrows are, but this is basically how you find the upper triangular matrix. The idea is each step you take, there's a new random site in the initial configuration that you get to look at that you haven't seen before. If you're going to the right, you have to look that way. When you're going to the left, you have to look that way. Okay, so this is true. Now, of course, that doesn't help because 2 to the t times 2 to the minus t certainly isn't going to give me exponential decay. So I have to just squeeze a little bit more out of it because this is critical. So there are lots of ways you could try to do this, but eventually we find one that actually works. So I claim if you take a given diagonal path, the probability that it's a leftmost or the leftmost diagonal empty path from the origin, you can bound it by something a bit better. So the idea is, if it's leftmost, then whenever it takes a right-left step like this, then that site has to be a 1, because otherwise it wouldn't be the leftmost path. So there's some more information if I know this path is leftmost. And, well, it turns out if I only restrict my attention to these right-left steps at odd times, then there is a dual assignment for them. So in other words, if I look at the whole set, the diagonal path, and these black squares that occur at odd times, then that set is uniformly random. You see uniformly random fair coin flips on it. And the key fact that you need, remember, you have to go back to the configuration starting from a single 1, and the key fact is that down this second diagonal you see alternating zeros and ones. So yeah, so it just works. So basically this allows you to squeeze something extra out of the argument and you get exponential decay. And yeah, I'll just show you the pictures, but I won't say anything. So for wide paths don't percolate, and it's a superficially similar argument, but in the details very different. We just had to find another construction that these dual assignments work for, and then proving that empty paths do percolate, again, uses a dual assignment, but in a different way. Okay, so then what do we want? So now I want to deduce. So what I just said was starting from randomness on all of z. So now I want to deduce percolation properties for what happens from a finite seed. So you take a random seed on a finite interval. And on the face of it, again, this seems more difficult still because the space-time picture I get is infinite, and yet I only have a finite number of bits of randomness to work with. But it turns out, I mean, this was somehow the surprising thing here. We were just always able to prove exactly what we needed and almost nothing more. So here's a simple result first of all. If you start from a random seed of length L, then there's, with high probability, there's no empty path from anywhere in the initial configuration in time 0 into this forward light cone by more than distance constant log L. And how do we prove this? Now we really exploit the long range dependence. So here's the picture starting from a single 1. If you look at a strip along the diagonal, strip of width k along the diagonal, then the picture that you see is periodic in time. And that has to be true for any cellular automaton, actually, because there are only like 2 to the k possible configurations you can see as you go down. But in this case, it's periodic with period order k. And that's because it's this special additive cellular automata. And, all these things like this, properties of this picture are easy exercises to prove, very easy exercises. So what that means is if you start from a random seed, again you have this additivity property, so this picture is simply a bunch of those superimposed on each other, chosen at random. Then again, this diagonal strip has period, same period as before, order k, order its width. And furthermore, if k is less than L, basically, each row of it is uniformly random. So at each time you see fair coin flips. But of course, there's a lot of correlation between different rows. So that's basically enough, because if there was a path from up here to somewhere in here, then it would have to go through this strip. But for every, each of these is uniformly random, so it's unlikely that you can make your way through it and down a bit. And the picture is periodic with period about k. So if you apply a union bound, then you don't need to look at infinitely many cases, you only need to look at order k cases. So you have the constant k because of the period, and you have the exponential decay. So this is small. And basically, by the same sort of methods, we can prove this. More elaborate application of the same ideas. Take the 1 or 3 rule started from a uniformly random seed, then with high probability, you have these triangular voids of zeros. Above each one, there's a strip which blocks diagonal paths. And by the way, everything I say for diagonal paths is true for wide paths as well. So there's a strip which diagonal paths cannot get through into the void below. And furthermore, all these strips are spatially periodic, so periodic in the horizontal direction, and with the same repeating pattern for all of them. And this is basically where the main theorem comes from, because if that's true, and you have one of these rules in our class, then within each of these voids, you're not influenced by what happens outside, up here. All you're influenced by is this strip, and this strip is just the same periodic strip in every case. So all you can get is an ether, the same ether in each void. And the way we prove that, again, it's just sort of a sequence of miracles, semi-miracles, just where you want them somehow. It's because in the configuration starting from a single 1, above each void you have a periodic. If you go a distance a power of 2 up, then you have something that's periodic with period 3 times 2 to the m, and it's this very specific periodic thing where you have 1, 1, 0 spaced apart with 2 to the m zeros in between. Again, anything like this, it's an easy exercise to prove. So it's not a mystery why it's true, but it turns out to be the thing we need. So that means if you start from a random seed, then you have something similar. Above each void, if you go up distance 2 to the m, you have something that's periodic, and the same period no matter where you look, and every interval of length 2 to the m within this periodic thing is uniformly random. That's the way to say it. So then it's essentially as before. And this is, so this is, as I say, this is what's behind the main theorem. So, as I said, somehow just enough things work to enable us to prove this, but many seemingly closely related questions we don't know the answer to. So, for instance, we do not understand very much about supercritical percolation started from random seeds. So remember, empty paths were in some sense supercritical, in the sense that if you start with random on z, then infinite empty paths exist. And the way we prove that is we actually prove a bit more that if you take all the points you can reach starting from, well, let's say the half line origin to the left, then it has a frontier, and that frontier has drift, positive drift a quarter. But for instance, what happens if you start from a random seed of length L and you look at where can you get to by empty path starting from the left-hand end, say? So here's an example of the picture that you get. Again, there's a frontier, and the question is, at time t, how far over has it got? And what we believe is that for typical seeds, this gap behaves like a non-trivial power law of t. Now that makes sense because remember, the black thing is essentially a fractal, and you presumably have speed a quarter when you're inside the fractal because it's kind of random, and you have speed 1 when you're in the voids. That part, at least, we can agree on. So, but it's a fractal, so most of the time you're in the voids. So that's kind of why this power law makes sense. But we certainly can't prove that. And again, it's not true for every seed. So here's a specific seed, and here, in the specific case, we can prove everything. If you look at this frontier, then it's a macroscopic distance from the edge. So even though, for a moment, we looked at these pictures for a while and we thought this must be essentially the same picture as this, because when you look at the first 1,000 iterations, it looks very similar, but it's not. In this case, this distance is this distance over t is strictly bounded between 0 and 1. And in fact, the frontier converges to a variant of the devil's staircase in the scaling limit. That's provable for this particular case. And we can prove that this power law holds for some very simplified version of the model that we came up with. And probably something like this power law is behind some cellular automaton pictures that we can't analyze. So here's an example for one of the rules in our class where probably what's happening is you have this frontier that obeys a power law, and then it causes some other things to happen just on the frontier. So if one could prove the power law, then it would prove this was a quasi-replicator, probably. And probably something somewhat similar is happening in this chaotic picture I showed you at the beginning. So again, this is one of the rules that our theorem applies to. So long random seeds are nice and predictable and well behaved. This one is apparently not, but presumably there's a power law frontier here and then all sorts of complicated things happening behind it. That's just a bigger picture of the same thing. So you can see there's this just tantalizing mix of order and chaos, because you sort of have this power law repeated in lots of places as well. And what's going on here? Well, it doesn't look exactly random. So nothing to say rigorously here. And also completely open are cases where the percolation is apparently critical. And this is a particular case like that. So, lots of open problems. I mean, we don't know how to prove that any of these rules have infinitely many possible ethers, although we believe it to be the case. Also, very interesting question is trying to do space-time percolation for other one-dimensional cellular automaton rules, not additive ones. And there are plenty of others, for example, Rule 30, for which uniform measure, fair coin flips, is an invariant measure. So that would be a natural place to start with some of these questions. So we don't even know what happens to empty paths if you start from random configuration on the half line and zeros on the other half. Of course, proving existence of chaotic behavior in any of these cases, very, very difficult apparently. Coming back to where we started, also presumably impossibly difficult. What does Conway's life do from a random configuration on Z2? And so the reason I think that's difficult is, on the one hand, you know, you can come up with these very elaborate computers that do interesting things, but they're not at all robust. If a little bit of chaos runs into one, then it's the end. But on the other hand, if you're on Z2, perhaps there are local configurations which do interesting computations and also are very good at defending themselves against attacks from chaos on the outside. You know, you have the whole of Z2 to play with, so and who knows whether those win over the chaos. So that's, yeah, that was sort of our motivation. But there I'll stop.
Questions or comments?
Do you actually prove that anything is not crazy?
No. Well, I guess strictly yes, but in a very trivial example. The one that was a different ether on the two sides, so it's a mixed replicator.
Oh,
I mean, this and this is more just a symptom of how we define things.
Okay.
But yeah.
Anything is not.
Right. That's right. There is a bit more evidence besides eyeballing the pictures than that, which is although it's roundabout evidence to say the least, the program I showed you right at the beginning for simulating Conway's life, it uses a remarkable, the program itself is called Golly, by the way, highly recommended, free software, uses this remarkable algorithm called hash life, which somehow stores configurations that it's seen before. And it's very interesting to see, so for some configurations it does very well. If you give it a replicator, it goes very, very fast. It gets into trillions of generations in a few seconds. For an apparently chaotic case, it's not much faster than just computing everything as you go, although it's a bit faster. And for quasi-replicators, it seems to be kind of intermediate. It gets into the millions. So there's kind of some evidence maybe there that the apparently chaotic ones really are more complicated than the quasi-replicators, but yeah, I mean, and I think that's something that could be investigated further.
Do you expect any classes of rules for which you would have the same behavior going outside? I mean, now you have everything dependent on three, taking bigger neighbors. You got any conjecture that if you take such and such a class, then that happens?
Yeah, I mean, one could formulate.
Because there are just too many rules. I mean, that's what bothers me. I mean,
That's right. Yeah.
why not take an 11 neighborhood?
Mm-hmm. Yeah, I mean, there's no. I don't think anything would particularly change if you started looking at bigger neighborhoods, but you'd just have to be very careful how to define things. And you know, all we're doing is
there any theorem which says that if your rule depends on a finite neighborhood which satisfies certain conditions, then you can encounter the following phenomena?
we didn't formulate such a result.
I mean, it does seem to rely very heavily on the fact that you've got this base fractal thing that you know completely.
Yes,
and then,
yes, that's absolutely
and then
essential.
deviations or the background just can't percolate in it.
Yes, yes, yes. I mean, really, we
examples with exactly that property.
yeah, that's right. I mean, yeah, the rules we prove things about are very, very special ones, and so one could extend the class of rules for which the theorems work, but it would still be very, very special.
An additive rule which you can study, and then something which is sufficiently flimsy that it can't percolate.
Yes, but sometimes it does, but typically it doesn't. That's what's new, really.
Thank you, Andrew, again.